start recording again. Now, let's look at the mechanistic principle of the electrophilic aromatic substitution. We also saw some examples of how, what kind of product you will be getting if you mix a certain electrophile with benzene. But as I emphasized, the mechanism is the most important thing in organic food. Certainly, we want to know how those reactant molecules react at the molecular level. Starting from the reaction state and go to the product state. And also, we want to have at least some qualitative idea about energetics of each and every step. So whether this step is either, let's say, three of possibilities, highly endothermic or highly exothermic, or it's not that, highly on, only endothermic or exothermic. Because of why it's important for us to know the energetics of each and every step, because of the energetics, mean whether it's energy exchange in elementary step is often associated with its rate. If a step, elementary step, is highly endothermic, that step almost always will be rate limiting. So that's why we need to know the energetics of each and every step. Okay? And you don't need to memorize. We can analyze, okay, whether a step is especially highly endothermic, highly exothermic. You can analyze. You don't need to memorize. Okay? If it's slightly endothermic or slightly exothermic, sometimes it may be hard to say. Okay? But if it's highly endothermic or highly exothermic, you can actually naturally analyze. You don't need to memorize. Okay? So again, we're going to use the mechanism of a reaction you should be very familiar with from organic one. Okay? So that mechanism, using that mechanism as a kind of a foundation for you to learn the new mechanism. Okay? So the old mechanism we're talking about is the electrophilic addition of alkene. What is the mechanism? Okay? So if assume the probably the best example we can use is let's say we have a hydrogen chloride, okay, react with propene. That's I can right here, okay. So if we have propene and then react with hydrogen chloride, so what will be happening? Okay, so because hydrogen chloride, as we know, is a very polar molecule. So I assume everyone the hydrogen is highly positive polarized and the chlorine highly negative polarized. And you have high electrons on the double bond, so makes the double bond nucleophilic. So you will attack the positive polarized hydrogen. And this kind of the attractive force between the negative charged electron and the positive polarized atom is often the major reason why two organic compounds can react. Okay? So here the negative charged electron is just pi electron. So this is a pair of electrons. Originally the bonding pair then become this curved arrow shows this pi bonding pair become one of bonding pair between one of those two carbons and this hydrogen. So that's the curved arrow shows. Okay, and hydrogen we know if based on the extended the octet rule, if it's bonded to something else, then this one has to come out. Okay, so this give you the this guy, carbocation, okay, and the chloride guy. So why this curved arrow only shows one of the two carbons will be bound to hydrogen, okay? But why it's the end carbon bound to hydrogen is dictated by stability of the formed carbocation, okay? Because when this carbon bound to the hydrogen, you get a more stable secondary carbocation. If this central carbon bound to the hydrogen, then you can have a much less stable primary carbocation. That's something we know organic 1. If you have difficult understanding, be sure to revisit organic 1. Okay. Now, I will be telling you this reaction, this step, okay, is highly endothermic. Why that's the case? Okay, because you have to look at the bond formation and the bond breaking in this the step. Okay, so in this step, what you see is two bonds will be breaking up. The carbon-carbon pi bond will be breaking up, right? And the hydrogen-chlorine one will be broken. Okay, both will be broken. Okay, but what bond will be formed? Only one bond will be formed. Okay, you're breaking two bonds, forming one bond. That must be highly endothermic. The breaking bond costs a lot of energy. Forming bond release of energy. Okay, so net effect, you are breaking one bond because you are breaking two bonds, forming one bond. So net, if you count the net bond formation, -1, you're breaking one bond net. Okay, so that's why this reaction is highly endothermic. You don't need to memorize. Just look at the chemical bond pattern. You will see. Okay, net effect is breaking a bond because you're breaking two bonds, forming one bond. Net breaking one bond. So it must be highly endothermic. So that's why this step is recommended. Okay. You don't need to memorize. That's the natural result of analysis. Okay. Then next step is basically the next step. What you see is this long tail. Okay. The chloride negative charge, the carbocation positive charge. The chloride has another negative around it, and the carbocation has central carbon positive charge. So the central positive charge carbon will be attracting the attack of negative charge chloride to give you the product. And in this reaction, if you look at the bond cleavage, bond formation event, you are net forming one bond. That's carbon chlorine bond. Okay, so that's why this step is highly what? Ectothermic. So it will be very fast, not rate limit. Okay. So that's how you analyze. That's what the older mechanism you should have learned in organic 1. This is a general spin, but I'm just using a real world example. You don't need to memorize. You can analyze. Okay. So similarly, when the 3 double bonds on the benzene ring react with the electrophile, one of the pi bonds, okay, will actually act as a nucleophile, okay, attack whatever electrophile, real electrophile you're gonna have in the in the reaction, and then the pi bond, okay, will bond to the electrophile, and this bond will break, okay. So this process, if you look at it again, if you analyze the energetics, this step has to be a highly endothermic step. Why? Because you are breaking a pi bond, okay? You are breaking a sigma bond between the electrophilic part and the nucleophilic part, okay? And you are only forming one bond. See, let me color code it. Let's say breaking bond, make it red, okay? This bond, you are breaking it, okay? This bond you are breaking it, okay? And the forming bond, let's say make it blue. You are forming this bond, Okay, so net event, if you count the bond formation not breaking one bond. So this is highly endothermic. You don't need to memorize, right? Just the look at the bond formation, you can see it. Okay, and if you can look at the energetics of first step from another aspect is the before reaction, this compound is aromatic. Okay, and in the intermediate, okay, the aromaticity is broken. This guy is no longer aromatic. Okay, so the substrate molecule lost aromaticity in this reaction. And aromaticity, we know, provides at least 100 kilojoule per mole stabilization, typically, depending on how you build it. Could be from 150 to 129 to 150 something, but at least 100 kilojoule per mole stabilization is a huge stabilization. So the loss of aromaticity also makes this step highly endothermic. So this step is always rate limited. And then next step, what you see is you are breaking CH bond, okay, and you are forming the HY bond, okay. You also are forming a pi bond. You see that? Let's say if we look at next step again, if that's color coded, breaking bond is red, forming bond is blue. Okay? So what are this color? This blue. Okay. So the forming bond, this is a forming bond, right? And here is another forming bond. Okay. And the bond will be broken. Is what is broken? Yeah, here. This one. So net bond breaking in the formation is net one bond is formed in the second step. So the second step is highly exothermic. Okay. So this mechanism we call addition elimination mechanism. Why we call it? Because if you look at first step is addition reaction. So the electrophile adds to the one oxygen double bond. This is called addition. This we call addition. This called elimination. So this is called addition elimination mechanism. And why we say elimination? Because in the second step you consider the Y minus act as a base, taking a beta proton from this carbocation. Because this intermediate is a carbocation, right? Positive charge carbocation. And this carbon is a positive charge, so this we call it alpha carbon. So this is a beta carbon. The base is taking a beta proton away, so it is a beta elimination step. Yes.
So what's it called? Benzene will always try to retain its aromaticity, right? It's not going to do like a pure addition reaction. So
yes. Because of very rarely you will see a successful reaction being highly endothermic. So this is overall reaction we're talking about. An elementary step could be endothermic. If the next step will release more heat than the first step absorbs. Okay? So from here to here, usually the reaction will be exothermic, slightly exothermic at least. Okay? But the first step is highly endothermic, second step is highly exothermic. But the heat released second step usually is more than the heat absorbed in first step. Okay? So the overall result still is exothermic. So yes, it's actually important. That's a very important point. Okay? Because aromaticity is such a great deal of stabilization. So the aromatic system, after losing its aromaticity, the molecule will try its best to regain its aromaticity because the molecules always want to be very stable. Okay, so that's why you see this first addition step, and in the second step, you quickly will lose the beta proton to regain the aromaticity. Obviously, this Y minus also can take the E away. Then if doing this, just going back to the starting material, it doesn't bring any change. That's change to the system. Okay. So I'm not saying this Y minus cannot take the E away. It will. Okay. But just going back to the starting material, reactants. No, it does not bring any change to the system. We don't need to consider that. It is happening, but we don't need to consider that. Okay. But the only thing we need to consider is the Y takes the beta proton away and give you the product. Okay. And there's a few ways to look at it. First is addition. In the addition step, you having a carbocation. You're forming a carbocation. This carbocation is a pretty stable carbocation if you compare to the carbocation we see here, because this carbocation is stabilized by resonance. This is a allergic carbocation. And let's say I'm gonna write just for you for this one time, but you need to be familiar with the process. Just say I'm gonna using one example. Okay, we assume that, let's say, benzene. Let's say oh, I'm not do it now. We'll do it later. Okay, but just just using more general one. Let's more general one. Okay. So benzene, you have the EY, EY. So this is black. Then place E here plus Y minus. Okay. So that is the rate limiting step. Okay. But this thing, okay, this guy, you can write multiple resonance forms for it. At least you can write is 3. So that is the second one, and obviously you can write so what you can see is this intermediate, okay, the positive charge at least delocalized over 3 carbons. At least, okay. You will see other more examples, the positive chemical delocalized over more atoms, but at least 3 carbons. Okay. So this carbocation generally more stable than the conventional carbocation. So this carbocation intermediate also has its name, a few names. Okay, we call one name called aluminum cation, and the other name called sigma complex. So as far as the pronunciation goes, sigma complex is easier to pronounce it. I just call it sigma complex. Okay. So because this is this intermediate. Okay, the formation of this intermediate is highly endothermic. Okay, so then it's we will see later. Okay, see, we can basically look at the general potential energy diagram of this electrophilic aromatic substitution is like this. Okay, and assume this is the potential energy of the reactants, and this will be potential energy of the intermediate. Okay, this intermediate have 2 names. we call, the can call it uranium ion, or we can call it sigma complex. You can use either way to call it. You also can call the full name cyclohexadienylcation. That's the full name. Okay, the uranium ion or sigma complex. You can use whatever way to call it. But for me, because I need to verbally deliver it, I think sigma complex is. Okay, you can call it whatever you want, but I will always call it sigma complex. So when I mention sigma complex, you better know what I'm talking about. Okay, so I'm talking about that, the intermediate. Okay, so why call sigma complex historically? Basically, the pi bond becomes sigma bond, called sigma complex. Okay? And if you look at this potential energy diagram, you see because the first step is highly endothermic. Okay, so the potential energy of this one, okay, is actually will be often dictating the rate of the step. That's determined by Hammond postulate. Why? See, what's the Hammond postulate says? Okay, means that if you have two successive states, usually one is transition state, the other one either will be reactant or the product. Okay, so if you have two successive states, when the two states, if they are similar in energy, they will be similar in structure. Okay, so obviously if you look at these two successive states or these two successive states, which two successive states are similar in energy is these two, right? Because this potential energy difference is so much larger. Okay, and these two states, their energy, they are very similar to each other in a sense, comparable. Okay, so that means the structure of this one is similar to structure of this one. Okay? So what does that mean? That means if anything makes this thing more stable, and the structural factor, if you change the fine tune the structure of this intermediate, okay, make it more stable, then this potential energy will go down, right? And the same structural modification, okay, will makes the the transition state also more stable, lower in energy. So what's the impact of the transition state to become more stable in terms of rate? If transition state become more stable, what will be the consequence of the rate? Will be faster. So that's this structure, okay? The sigma complex structure stability is of huge importance. The greatest importance in this chapter, actually. Understand the structure of this, how structural factors impact the sigma complex stability. Because if you can make sigma complex more stable, then its corresponding transition state will be more stable by Hammond postulate. If the transition state is more stable, then the rate will be faster. And this step is a rate limiting step. If this step is faster, the entire reaction is faster. And similarly, if you make this one say, oh, energy going up, okay, become less stable, right? Then this thing, all energy goes up. Okay? Then the transition state becomes less stable, means the rate becomes slower. The entire reaction will be slower because this first step is rate determinant. So this one, understanding the structures of the sigma complex structure is of huge importance, and one crucial instrument you can use to understand the sigma complex structure is resonance. Okay, so you will need this instrument to aid your study. Okay. This is one thing. The other thing is, okay, again, if as you can see, from here to here, okay, is high. You have pretty high activation energy, okay. So that makes such a reaction requires a highly electrophilic electrophiles, okay. So then next step we will try to proceed to understand the nature of the electrophile and each and every reaction. So what is the real electrophile in each and every electrophilic substitution reaction. Okay. So that's a recap of the general mechanism of the benzene reacting with the electrophile. So the reaction follows a two-step mechanism. And the first step is electrophilic addition to the electrophile give you a sigma complex. And this is the highly endothermic and the rate determinant step, this addition step. Okay. The second step is the elimination of beta proton from that sigma complex, give you the the final product. And this step is highly exothermic, so it's not rate limited. So this called addition elimination mechanism in general. Okay. The other way to view it, again, can reinforce the view of first step being the rate limiting. Is in the first step, if you look at the keep your eye on the aromaticity of the substrate. In the first step, you're breaking the aromaticity. Okay? You're breaking the aromaticity because of here you have 6 pi electrons in a single ring, satisfy Hucker's rule. Here you only have 4 pi electrons because of the other one becomes sigma. Okay, so no longer aromatic. Okay, so this breaks aromaticity. So that's why also enhance the its nature of being highly endothermic. The second step, because the molecule tries to best to regain its aromaticity. So why they want to undergo beta elimination, losing the beta proton, because after losing beta proton, you can regain the aromaticity. So it's very happy to do that. And the extremely important intermediate we call the sigma complex, uranium ion or cyclohexadiene catalyst. Now based on this potential energy diagram and application of the Hammond postulate, the stability of sigma complex is of the highest importance, in this chapter of the standard rate. Okay. So this not only true for the electrophilic aromatic substitution reaction, also true for nucleophilic aromatic substitution reaction. So so this one's of this guy's stability is of crucial importance, and also because the first step is rate limiting, you have a high activation energy. So it requires a pretty powerful electrophile that we're going to look at what kind of electrophiles are involved in each and every type of basic electrophilic aromatic substitution reaction. Yes?
So the sigma complex basically dictates like whether the stability of the transition state, and that the more stable it is, the faster the reaction.
Right? Yes. And how do you know which sigma complex will be more stable, less stable? You have to look at resonance of. Okay. Now first, let's look at the nitration of benzene. We already talked about before nitration of benzene. You have nitric acid react with benzene. They become natural benzene. Typically, this reaction, the rate is slow without catalyst. And the catalyst that we need to use is usually just sulfuric acid. Sulfuric acid. And we will explain, why we need a sulfuric acid to speed up the reaction. So the reason is why we need a sulfuric acid to speed up the reaction is the really active electrophile in the nitration reaction is the nitrogen cation. Remember, I wrote it as this one, the NO2 and the OH. Okay, so the OH is the nucleophile part, and NO2 is the electrophilic part. Okay, but this, this view has been, was experimentally confirmed that really active electrophile is NO2. NO2 plus. Okay, so is the nitrogen cation. So if you look at nitrogen cation, if you look at Lewis structure, it's just I think I should go back to red. Is NO you have lone pairs on the oxygen, but there's no lone pairs on the nitrogen. So there's there's one whole unit of positive formal charge on the nitrogen. So as you're gonna see later, this electrophile is among the most powerful electrophile you will be seeing in this entire course. Why? For a few reasons. Okay. First, the electrophilic atom is a nitrogen atom. So as you're gonna see later, this is a very electronegative electrophilic atom you will see, because often we will see electrophilic atom is a carbon often. Okay, and nitrogen is substantially more electronegative than carbon. So this is one. This is because of nitrogen is electrophilic atom. Second, you see the nitrogen has a whole unit of positive charge on it. Okay. Third, we have two oxygen double bond to nitrogen, and that means oxygen is the second most electronegative element. So the two NO double bond also pull away electrons away from nitrogen, makes nitrogen very, very electrophilic. Okay, so that's the nitrogen cation. It's one of most powerful electrophiles. It's most reactive electrophile. One of. Okay. I don't want to make absolute statement, but it's one of the most reactive electrophiles. So you will react with any aromatic group you will be given. So why you need a sulfuric acid to catalyze the reaction? Because of the nitric acid itself, its standard ionization can produce a bit of proton and the nitrate ion. Okay, that's the normal ionization. It does not produce any substantial amount of nitrogen cation. See, if you know the nitric acid, I assume you know the nitric acid. Generally, HNO3, okay, you can ionize, give you a bit of proton, okay, and NO3 minus. The standard ionization, okay. The major the electrophilic species in nitric acid is the proton, not nitrogen cation, okay, not nitrogen cation. So how do you enhance the nitrogen cation to make this reaction pathway fast enough? One thing you can do it at a sulfuric acid, because sulfuric acid, if you check the pKa table from organic 1, sulfuric acid is sizable stronger acid than nitric acid. So nitric acid, although is considered one of 3 commonly used strong acids in a chemistry lab, but if you look at pKa value, it's a borderline strong acid. The pKa is, I think, that's minus 1.5 or minus 1.4. It's very similar with hydronium ion. So nitric acid is a borderline strong acid. Sulfuric acid is substantially stronger. Okay? So that enables sulfuric acid to protonate the nitric acid. So this protonation, it happens to sizable extent. Then again, you see if the OH group is protonated, okay, then you have water, okay. Water usually still molecule can live, okay. And besides, there's another property you might know of sulfuric acid. If the sulfuric acid is concentrated, it's itself is a powerful dehydration reagent. So if you put a drop of sulfuric acid on paper, if you have a solid in paper, you will see that the paper will turn brown, eventually black, because of sulfuric acid can take the water from the in the paper you don't have the molecular form of water, you have the hydrogen group and hydroxy group in the paper. Then the sulfuric acid can take those hydrogen and OH group, basically promote elimination reaction and make this one into carbon, brown even into black. And the similar thing, sulfuric acid, because of powerful dehydration reagent, can remove water and leave the formation of nitrogen cation. So because adding sulfuric acid encourages the formation of nitrogen cation, so that's why sulfuric acid can be a catalyst for the nitration, okay? Because it increases active electrophile concentration. Now, I'm gonna do it one time for the entire, the mechanism for the nitration. Assume that, yes, your question.
Yes, about the previous.
Yeah, assume nitrogen cation is the electron. Yes.
Does this only apply to like protic acids? What if it's aprotic, you don't have to use like a strong acid to protonate the OH?
Oh, so this add sulfuric acid only applicable to nitric acid as a nitration agent.
So not even protic acid, just specifically nitric acid.
Yeah, because let's say if it's the hydrogen bromide, okay, adding sulfuric acid, because hydrogen bromide has the key part is the sulfuric acid has two goals to play here. One is stronger acid nitric acid. Second is dehydration reagent. So if the dehydration reagent, you need the OH group in the acid to lose the water, and the hydrochloric acid don't have a OH group in the acid.
So there's just a smaller mechanism happening within the larger.
Yeah, this basically just the mechanism to explain why adding sulfuric acid can enhance can give you more nitrogen cation. So the key part is here, the nitrogen cation is real electrophile, and adding sulfuric acid can increase the concentration of nitrogen cation, therefore makes the reaction fast. That's why sulfuric acid is so chemical. Yes. Oh, okay. So anyway, so that is how I'm gonna just draw the things here. I'm gonna just show the entire mechanism. So I hope you're gonna draw with me so that so you can basically know this thing a bit better. So this, okay. So that is the rate limiting step, slow step, and then the obviously you're gonna have the say you're gonna have base in the system here. Obviously you're gonna have water here because of the sulfuric acid take water from the nitric acid. So water you can serve as the base here. So the second step is pretty fast reaction. Now, sulfonation of benzene, the real reagent, okay, is the real electrophilic reagent. Is not as clear cut as in the nitration, but most of studies suggest that SO3 is the real, the electrophilic reagent, in sulfonation reaction. Sulfonation reaction basically benzene react with sulfuric acid. So this has been experimentally confirmed by the fact that if you add SO3, sulfur trioxide, into sulfuric acid, then you can substantially speed up the sulfonation reaction. And the mixture of the solution of SO3 in sulfuric acid called fuming sulfuric acid. Basically, if you open it, the SO3, although it's a low boiling point, it's actually sublime. Okay, it could be a solid at the temperature slightly below room temperature, but once open it, it can form gas, and then it in contact with the moisture in air, it forms sulfuric acid. So if you have the SO3 dissolved sulfuric, they have a fuming sulfuric acid, and there is more powerful sulfonation reaction than pure sulfuric acid. So that is basically this support the idea SO3 is a real sulfonation reagent. Okay, and even you don't have SO3, if you don't purpose add SO3 sulfuric acid, it's believed that if you have a concentrated sulfuric acid, and the sulfuric acid can lose a little bit of H2O, give you SO3, small amount of impure sulfuric acid. Okay, so basically SO3 is considered as the sulfonation, a real the electrified sulfonation reaction. So after the real electrophile has been identified, the reactions are the same. You have benzene, the pi electrons make the the benzene as nucleophile attacking electrophilic sulfur atom because of sulfur is sensibly less electronegative than oxygen. And the sulfur connect to 3 oxygens to make this sulfur actually pretty electrophilic. Okay. So this is basically the rate limiting step, give you this sigma complex. Then this sigma complex can react with the base here, and here the base is we consider just the conjugate base of sulfuric acid, hydrogen sulfide ion as the conjugate base. Take a proton away, give you sulfuric acid, and this called benzene sulfonate ion. And the last step is just the proton exchange, and this is actually a reversible reaction because of the final sulfonation product called benzene sulfonic acid is a strong acid, which is similarly strong as sulfuric acid. So you're gonna see in real mixture you have this and this, both could exist. Okay, so it doesn't matter. Now in case of halogenation, if we don't use catalyst, say you have mixed pure bromine or chlorine gas with benzene, the reaction is very, very slow. You will need a catalyst. So the real active catalyst is something can make the halogen more electrophilic. So why this case? See, okay, we know the halogen here serve as the electrophile, okay, and this one is nucleophile. So if you want the reaction faster, either you can use a better nucleophile, but if you don't want to change if the benzene is a substrate, is something you can modify it, right? You cannot do anything with it. So you have to do something makes this electrophile more electrophilic. So how do we make it more electrophilic? How to make something more electrophilic? Steal some electron density away from this thing, right? If you steal some electron density away from the electrophilic reagent, then this electrophilic reagent will be more electron hungry, right? Does it make sense? If something you want to make it electrified more electrophilic, means you make this reagent has more appetite for electrons, right? So if you take some electron density away from this thing, you're gonna have more appetite for electrons. So basically, you have steal some electron density away. So what things can steal electrons away? Yeah.
More electronegative.
Yes, more electronegative could, but that have to be covalent bound to it. So yes, positive charge things you could. Very good. That's all good things. But if you want to get the positive charge, the reagent may not be easy. Okay? So more practical, the approach. But your approach is correct. Yes.
Be a metallic ion.
You have some Lewis acid. Because Lewis acids, they are by definition, they are electron pair acceptors. So if you add a Lewis acid, the Lewis acid will try to steal electron density away from your electrophile, then the electron part will be more electron harmful, make more. That's the general idea. So there a few Lewis acid can be used for that purpose. One most common one is that it can be used for that purpose is alumina chloride. This is a strong Lewis acid, but also very cheap. For whatever reason, you just burn alumina metal in chlorine gas, you can get it. Okay? So it's commercially inexpensive and very powerful Lewis acid. You can use that for this purpose. You actually can. Okay? And but the problem with this one is that you have to using it completely anhydrous form. So you have to keep it very well away from moisture. If you don't seal it well, will lose its activity very quickly. So this it can be used, but the more convenient one is you could directly using iron 3 chloride or iron 3 bromide. Okay, so those two guys they are a bit weaker Lewis acid than this one. Okay, but in most of reactions, this one is strong enough to speed up. Okay? So these two are really commonly used. And even better is you can simply throw in some iron powder in your reaction mixture. Because iron powder can directly react with chlorine or bromine and give you the iron 3 bromide or chloride in situ, just on site. So although you in the reaction add iron powder, but the real catalyst iron bromide or iron 3 chloride.
So it's the iron 3. So it's the iron 3 bromide that acts as a catalyst.
Yes, it's basically iron. It's two iron in the mixture. The iron will react with bromine, bromine or chlorine, give you iron 3 bromide or iron 3 chloride. Those are real catalysts.
So then what does the iron 3 bromide do exactly?
Well, that we can talk about next class because I already think I 956. Okay, so I will upload the lecture for next class. Okay, then yeah. Oh, yeah, because of the iron 3 bromide chloride, because they are